Okay, welcome to the Graphs and Matroids seminar. Today our speaker is Kathryn Nurse from Simon Fraser University, and she's going to tell us about a new beautiful proof of Seymour's sixth flow theorem.
Okay, thanks. I'm happy to be here. Thanks for the invitation. And I just hope this talk is going to be a nice kind of an easy talk. And I hope that you ask questions throughout the talk. It makes it easier for me, and it's a little bit more of a back and forth. So feel free, if you're comfortable, to do that at any time, just interrupt. This is a joint work with Matt DeVos. He's my supervisor at Simon Fraser University. Okay, and I just did the slides this way so that I would be able to write easier and have all my colors. Okay, I just want to set up a bit better. Okay, so for this talk, I'm just gonna give a quick recall of the definitions about what nowhere zero flows are, and I'll give a short history of kind of the area, and then I'm gonna cover some easy observations, and these observations we need for the proof, but they're all easy and straightforward. We just need to use them, and then I'll give a proof that every two-edge connected graph has a nowhere zero flow in Z2 cross Z3. And then I probably will disappoint all of you and show you that it's really just a repackaging of Seymour's original proof. Probably people have noticed this. And then I'll show how you can maybe specify some of the flow out of vertex. And this it's the same proof as Seymour's original proof. So you can do that with his proof too, I think. And then in the paper, we didn't actually write up how to convert a modular flow to an integer flow, which is the sixth flow theorem. It's an integer flow. So if there's time, I will just, I'll give a quick explanation of how to do that. Any questions? Okay, so what is a flow? I want to think about a flow on a graph, and it's an orientation of the edges, and then an assignment of flow values to those edges so that the flow in equals the flow out at every vertex. This is like a very loose definition. And so I'll just give an example of a flow. So here I have a graph. I have an orientation already, and I give some values to the edges. Maybe 1, 1. Okay, so I assign flow values and integers to these edges, and then you can see at every vertex, as long as I did it correctly, the flow out is equal to the flow in. And then this is actually a nowhere zero 3 flow. We say it's nowhere zero because there's no zero on any of the edges, and we say it's a 3 flow because the absolute value of every flow value that I put down in the integers is less than 3. Okay, so okay, and then it's also a nowhere zero Z3 flow. So we can do flows in groups just the same way, and because it's the flow in is equal to the flow out at every vertex in the integers, it's also equal in Z mod 3 because you just get 0. Okay, but we can, there's kind of more flows that you can put in modular flows. Like I can change this to, maybe I want to put a 1 this way instead of the 2. And then I get that this is a nowhere zero Z mod 3 flow, but it's not a nowhere zero 3 flow. It is a case though that if you have a nowhere zero modular flow, then you have a nowhere zero integer flow, and that was the thing I was going to talk about at the very end. The other important thing to notice is that we can reverse the orientation of the edges. So I can switch this edge to go the other way, and I put the additive inverse on that edge, and it still preserves the property that the flow in is equal to the flow out at every vertex. So really having a nowhere zero flow is a property of the underlying graph. Okay, and the last thing I want to say is that I may talk about the boundary at any vertex, and that is equal to the flow out minus the flow in. So then the boundary at these vertices, I'll write them in the integers. So at the top vertex here, you have the flow out is 0, the flow in is 3. So the boundary is -3. Down here we get 3, and here we have 0 and 0. So when I talk about boundary, I'll just say that's the boundary. Okay. Any questions? Too easy. Okay, just a short history. So in 1954, Tutt showed that every planar graph has, he showed that, Tutt initiated the study of nowhere zero flows as a dual notion to vertex coloring. And so basically, he noticed that in the plane, a graph has a nowhere zero K flow if and only if its dual has a proper K vertex coloring. And he showed in this nice paper, he showed that kind of the equivalence of having a nowhere zero K flow and a Z mod K flow. And he did that actually for any abelian group. He also made his 5-flow conjecture there. So the conjecture is that every 2-edge connected graph has a nowhere zero 5-flow. At the time that he made that conjecture, it wasn't known for any constant value. And so he had also a weak 5-flow conjecture. And then that weak 5-flow conjecture was proved by Kilpatrick and Jaeger in 75 and 79. And they showed that every 2-edge connected graph has nowhere zero 8-flow. And they did this by basically they bumped up the connectivity. You kind of get this for free to 3-edge connected. And then they found, and then they kind of doubled the edges. They found 3 disjoint spanning trees. Those exist by other theorems, I think from Tutt, and I think it's a Matroid thing. But then they use those disjoint spanning trees to get the nowhere zero Z2 cross Z2 cross Z2 flow. And that was the same as finding any flow. Okay. And then just like 2 years after Jaeger, Seymour published his proof of the nowhere zero 6-flow theorem. And then there's been a lot of progress since then on like the 5-flow conjecture, but obviously you can't get anywhere between 6 and 5 without getting straight to 5 because we're working in the integers. So progress has been kind of in other ways, like, I don't know, like showing that like the minimum counterexample has a high girth or something. Okay. Any questions about the history? Everybody knows everything. Okay.
No, actually, I do have a question. Sorry, Kathryn. I wasn't aware of this Kilpatrick thing. I actually don't know who Kilpatrick is. So what's the story there? Is that in the thesis or something? It seems to be
it's in
a thesis.
Yeah, it's in his master's thesis, actually. It was a master's thesis. And I know about it because Matt told me, and it's hard to find. I actually haven't found it.
Okay.
Yeah, but they didn't know about each other. Jaeger didn't know about Kilpatrick.
Isn't Kilpatrick an Australian?
That sounds right. I'm not too sure. I can tell you. Do you want me? I could post it to the.
Yeah, that's fine.
Okay. Okay. And now I'm just going to go over some easy observations that we need, and then we'll do the proof. Okay. So the first observation is that the flow across any cut is 0. The net flow across any cut is 0. And I just drew an example down here. So this is the edge cut, and the flow across this edge cut is 0. You can see this pretty easily a few ways. The flow across the edge cut is just the sum of the boundaries, the vertices on one side of that cut. The boundaries are all 0. When you sum them, you get 0. You can also see that every edge inside my edge cut, it contributes 0 to the sum of the flow boundaries that you get. Yeah, I explained that badly. Okay, this is kind of an easy, straightforward observation, but we're going to use that. So the second thing is that we can contract an edge, and we preserve that we have a flow, and we also preserve that the flow is nowhere 0 when we contract. So and that just comes because this is an edge cut, and then when we go to contract that edge, we have this part. These are all the edges that were in the edge cut upstairs. And so the total sum across any edge cut is 0, and that means you can contract an edge and preserve that it's a flow. And also, if it was nowhere 0 up here, then it's the same value down here. Okay. The third one is that you can uncontract an edge, and this kind of just makes your problem harder. You preserve the property of having a flow, but you don't necessarily preserve that it's nowhere 0. So here I just did here. So I have this pink vertex, and I want to uncontract it to this edge here. And if I do it this way, where I go straight down, I look at what boundary I get on the vertices when I just uncontract this one edge. So the flow out minus the flow in is -3 on the left, and it's 3 on the right. These are additive inverses of each other. Of course, that has to happen because the total flow across the boundary has to be 0. And so what we can do is we can, oh, great. I want to put a flow of 3 going this way. I'll just erase the boundary so it looks prettier. And so this, you always have a number that you can write down so that it's still a flow, but you might not be able to write down a non-zero number. So if you go this way on the right side, you can see that the boundary on each of the 2 vertices that you get is 0, and so you're stuck writing a 0 down. So when you uncontract edges, you always can preserve the flow property. So you always can uncontract all you want. You just may screw up and get nowhere 0, or not get nowhere 0. You might have to write 0 down sometimes. Okay. Okay, and then there's kind of the saving grace that you get. Actually, if you contract a small cycle, if the cycle has size smaller than the size of your group, then you can always fix things so that you preserve the nowhere 0 property. So over here, I drew this vertex. Sorry, this part, I want to uncontract this vertex into a cycle of length 4. So I get this one, and I didn't draw any numbers. I uncontract. I know I can write down values so that I get something that's a flow, but I'm in trouble if I get a 0. But this cycle has kind of a flow that I can put around the cycle. I can put a flow of 1, or I could put 2, or I could put 3, and I can do this. Let's talk about, say we're in a group Z mod K. I can put 0 all the way up to K minus 1 kind of around this group. So I have the same number of choices here as I have the size of my group. And each of those choices can, screw up an edge, but only one of those choices screws up each edge. So this edge here can get screwed up by one of those choices. This edge can get screwed up by one of those choices. And if I have more choices than edges, then I can always fix things so I never have 0. Did I explain that okay? Do you have any questions? Okay, perfect. Okay, and so this we're gonna take advantage of in the proof. Okay. Okay, yeah, so now we'll just give this proof. So what we do is we just kind of bump up the induction hypothesis a little bit. And so we have, if we have this graph, it's 2-edge connected, and we have the special vertex U. And at that special vertex U, we're going to specify the flow. And so we're going to work in the group Z2 cross Z3. And we're going to say at our vertex U, it's completely 0 in Z2. So the Z2 flow doesn't really get to touch our vertex U. And that means that it's contained in the support of Z3. So we'll just draw, this is all that we're doing. We have a vertex U, has some edges, and then all of these edges are contained in the Z3 flow. They're in the Z3 flow, and then what should we do? Pink. They don't have any Z2 value, like it's 0 for Z2. So that's what the statement means. And then we prove this by induction. Okay, so this will be by induction on the sides of the vertices of the graph. So our base case is just a single vertex. So if you have a single vertex, sorry, I also need to say, we're allowing multiple edges and loops. So those are not usual to allow, but it just kind of makes the statement easier. They don't really change the problem significantly. So okay, so if we just have one vertex in our graph, that's our vertex U. We need to put a flow on the edges incident to that vertex. They're only going to be loops. That flow needs to be totally contained in Z3, but that's fine. We can just put, you know, one on all of these loops, and then the base case is done. So that was easy. And so now we move on to the induction step. So we have at least two vertices in our graph. And now what we want to do is we consider two cases. So we have our graph on our special vertex U, and we considered G delete U. And then we'll have two cases. So either this graph G delete U has a cut vertex or not. Okay, so basically, I've already drawn differently than I planned. So I have this vertex U, and this will be case A. So G delete U has a cut vertex. So that means I can find in the graph without U. I'm already saying things badly. I meant to say cut edge. Sorry. Okay, so it has this cut edge E. Okay, and then U, because this graph is two edge connected, U has an end in each side of the edge cut. And then of course, like there could be more to the graph, but I'm not going to draw it. So basically we found this, we found two edges incident to U and this edge E, and we're just going to contract things. So we're going to contract this side. We just contract all the edges on this side, and we make that into a new vertex U prime. And then this could have more edges. So we get two smaller graphs, and then we'll contract this side over here. So this is graph. Okay. So basically, we just contract the two sides, and now by induction, so we've contracted an edge for sure, because I showed that these edges here and here exist, and so there's at least one. We did contract something. We did make our graph smaller. It has less vertices, and so then on each of these two parts, we can apply our induction hypothesis, and then we get that the edges here are edge E. These edges are all contained in the Z3 flow, and they're not in the Z2 flow. And now we've kind of almost finished this case. We can just take the flow that we get on each side and say that's the flow that we get in our bigger graph. But there could be one problem. One problem is our edge E. If our edge E, maybe it has a different flow value. E is the only edge that's in both of my subgraphs. And if I have a different flow value in Z3 on the edge E, then I've screwed up. I can't just combine the flows and say that they're a flow together. So we need to make sure that the flow on the edge E is the same on both sides. But this is just very easy because the flow is in Z3 and it's not in Z2. Z3, it just has three values. And so maybe the only way we can screw up is if we have one here on this edge E for you know, the same direction, and then -1 here. But what we can do is just multiply our flow on one of the sides by -1, and then we get that they agree on the edge E. So I changed the flow. So this becomes a 1, and then now we just combine them, and then we get a flow up here in our bigger graph. Okay. Any questions about that case? That was the easy case. Okay, and so now what we're going to do is assume that the graph G delete U doesn't have a cut edge. Okay, so I'll draw the graph. So we have our vertex U, and we have the rest of the graph. I'm not going to draw the whole thing, but I have some components of G delete U. It could be just a single vertex. And this component of G delete U, because we're 2-edge connected, there's at least 2 edges that go between U and this component. And it could be, and I'll draw this, maybe I'll call X. This is X prime. Okay, and it could be that X equals X prime, that is fine. And so now this component is 2-edge connected. Okay, and so that means that there exists 2 edge disjoint paths between X and X prime in that component. Okay, so they could be empty paths because X could be equal to X prime. They don't have to be vertex disjoint, but we get some kind of like nice paths between the two. So what I've drawn here, I'm going to call this like my subgraph H. It's an even subgraph. Every vertex has even degree. Okay, and we get that just because of 2-edge connectivity. And now we're going to start contracting, and we're going to move from, this is our graph G. I didn't draw the whole thing, but it lives in our graph G, and then we're going to move to our graph G prime. I'm just going to make this a little bit. A little better. Okay, then we go from G to G, we'll call it G1, and then we're going to go from G1 to G2. So to go from G to G1, we contract the edges in H. So G1 equals G contract the edges in H. And H is the even subgraph that we found on the left. And then to get from G1 to G2, we're going to contract these edges. We'll do a different color. So that there could be more than 2 edges. Can have any number, at least 2. And those are edges S. They go from U to H. And so G2 is equal to G contract S. And I'll draw it. So this is U. Okay. And so this lives in kind of a bigger graph. So we need to make sure that we got smaller, but of course we got smaller. We may not have gotten smaller here, going from G to G1, but we definitely got smaller when we go from G1 to G2, because X and X prime are not equal to U. And so we got smaller here. And so in this graph, by induction, this has the flow that we wanted. And so I'll just scroll up for a second. So at U, remember the flow is on the edges incident to U. They're totally in Z3, but they're not contained in Z2. So these, you may have like edges going to the other parts of the graph. We can have loops because we may have contracted things. We can end up with loops, but all of those edges are contained totally in the Z3 flow, and they're not in the Z2 flow.
So you mean contraction? G1 and G2 are contractions, they're not deletions, right?
I'm contracting, yes.
So why,
Sorry.
why is it marked as a deletion? It looks like
Because I screw up. Sorry. I always get that wrong
okay.
when I write it.
Okay.
Sorry.
Thank you.
Yeah, no, thanks for pointing that out. Any other questions or things that I did? Okay.
I have a quick question.
Okay.
Is there a reason why you don't just take 2 edges in S? Like, why do you take them all?
Well, yes, I need so we need the edges in S to end up not in the Z2 flow. So if we don't take them all, they end up as loops, and then you're fine. So I don't think I need to take them all. I think I could just take 2.
Yep.
Yeah. So
Okay.
sorry, you're right. You could just take 2. You could take them all too, though.
Yep.
This is the same. Yeah. Any other questions? Okay. Okay. Right, so here we have our new vertex U prime, and we have all the edges incident to U prime are contained in the Z mod 3 flow. And now we go back on contracting. So we uncontract first the edges in S. And so we want to move from G2 to G1 here. And so when we uncontract, the edges in S are not going to get any value except for 0 in Z2. We can just, the Z2 doesn't touch the vertex U. We uncontract here. The Z2 flow exists outside. It's this nice little bubble. So the edges in S are not in Z2. They're 0 in the Z2 flow. And then they can have some Z3 value. We uncontract, we know we can write something down in Z mod 3. Like I said before, we could have some 0 edges, except the thing is, and maybe it would actually, the way Jim said, would be easier if we only take 2 edges. But I wrote it this way. So we have maybe some edges that are 0 and some edges that are non-zero. But we can always fix those 0 edges by just adding a flow of either 1 or -1 on these kind of, oops, here, these kind of little cycles here. So we can always fix each edge. We could just do it one at a time. And yeah, Jim, your way is definitely better. Just 2 edges is easier. Okay, and so now we have the property that all the edges in S are in the Z3 flow. They're contained in the Z3 flow, and they're 0 in the Z2 flow. And so now we just have to uncontract our vertex H. And so we go again this way. We uncontract H, and this the same thing happens again. Our vertex, all of the edges incident to that vertex in G1 were not in the Z2 flow, and so we have no Z2 flow value on any of these edges. It's all 0, and we write some value in Z3, but this time we fix it. So we're allowing 0 in Z mod 3, but now this time we can add, because we've chosen H to be an even subgraph, we just take an Euler tour of this graph. I just want to see what color I wrote for Z2. I picked pink. So an Euler tour of this graph, we just basically go around this way and put 1 on all these edges in our Z2 flow. And so these edges in H, they may be in the Z3 flow, but they're certainly in the Z2 flow. And so once we uncontract 2 times, we're back to our original graph, and every edge is covered by the Z2 cross Z3 flow. And that's it. Are there any questions? Okay. Okay, now I will show you why it's just a repackaging of Seymour's original proof. So what Seymour did was he found a list of cycles here. I've just drawn it, this list of cycles. And he found this, oh, so sorry, the first thing, reduce to cubic. And when you reduce to cubic, you get, sorry, I guess that's 2. I think he has to reduce to 3 edge connected. And this is kind of a straightforward argument. And then you reduce to cubic, and then once you do both of those things, you actually get 3 vertex connected. Okay, so he finds this kind of tower of cycles, and what he does is he puts the Z2 flow on all the edges in the cycles. And then on the edges that aren't in the cycles, he puts the Z3 flow. And so he has the same kind of thing. The edges in the cycles, they're in Z2 and they may also be in Z3. For these edges. And then these edges here are in Z3, but not in Z2. And so actually Seymour's proof, it's beautiful. You can start with any cycle in the whole graph. And he also, these cycles can also be generalized cycles. So they can also be just a single vertex cycle. And so if you start Seymour's proof, kind of building the bottom of the tower, you start it with this, just a vertex. That's your vertex U. And then Seymour finds, you know, the next cycle has at least 2 edges to U. Those are our edges S. And then this kind of first cycle is our subgraph H. So it ends up kind of being the same thing. It's the same proof. Any questions about that? Okay. Okay, one thing, when we did this, we actually proved it differently, and then Matt saw that we didn't have to do it this way. But what I wanted to do, like, first, I was kind of trying to specify the flow at every vertex, and so you can actually say this, but you sacrifice a lot of simplicity. But you can say this thing. You can say that at your given vertex U, you can choose a set of edges S. S will be blue, incident to U, and as long as you pick an even number of edges that go to each component of G delete U, then you can say, well, the edges in S are the edges contained in my Z2 flow. And then the edges not in S are, those are all contained in the Z3 flow, but not the Z2 flow.
So your argument just takes U out and looks at the separate components that you get, and then puts U back in, and basically just deals with that. That's what it is, isn't it?
Yes. The up here?
Yeah.
Yeah. I think what you're saying is, what you mean when you say take you out?
Well,
you basically.
Yeah. Go ahead.
I actually don't know what I'm saying. But when you say take you out, like you can't just delete it, but you kind of do take you out of the Z2 flow.
Okay. Okay. Thanks.
So James, I mean, it's just 2 edge connected, not 2 vertex connected, this thing. So for this picture at the top, for example, she's just throwing the other blocks in, like you can throw the other parts wherever you like.
Okay, thanks.
Oh, yeah, sorry. I just, for the sake of clarity, I was trying to not draw all of the like all the extra parts of the graph. Is this what has happened here? Yeah, it's not two vertex connected. So there are other, I mean, you can have other components. But yes, sorry, like you said, Jim, that you just kind of tuck them into one of the sides for this argument. Sorry. Okay. Sorry. Are there any other questions about this? Feel free. Okay. Yeah, so here I'm just trying to say that you get a little bit, you can instead of saying at the top, what I said was that basically I was coloring all of the edges incident to you green, and I'm saying that you can color some of them, the edges incident to you blue. And by blue, I mean they're going to be in the Z2 flow. And you have to be careful when you do this. You can't pick an odd number that go to some components, because then this, right, this is an edge cut, and you have in Z2 the flow across that edge cut is not zero. So you always have to have an even number, but as long as you do choose an even number, you can specify this. And so what this is doing in like your sixth flow, when you kind of do the conversion and convert things, the edges in blue end up being odd values. So in their sixth flow, you get 1, 3, 5, and the edges in green, you get the even values. So 2 and 4. And so the argument is basically the same, but what you, I'm gonna just add a couple more blue. In every component, you end up getting 4, sorry, not 4, an even number of vertices that are adjacent to you by an odd number of edges. So if I have double edges, I'm gonna kind of ignore them. Like this, I can just, I can kind of fix this by putting the Z2 flow on it. So I'm gonna, and I just pretend they're not there. Let's just do this for the sake of simplicity. Like this argument is not the simplest. It's still pretty simple. But so basically what I want to look for in this graph is, I'm gonna find a graph that has odd degree on every vertex that's kind of in my end of one of the edges, and even degree everywhere else. So this is a T-join. And they exist because this component is connected. And so basically, once you find this, then this part, you take your T-join combined with these edges, and that's an even subgraph. And so you kind of, you contract that. All of this together. I'm not going to go through the whole argument, but you contract all of it together, and that's your even subgraph. And then so that even subgraph you have in the support of the Z2 flow, and then the rest of it is in the support of the Z3 flow. I just, yeah. Do you have questions about this?
Yeah, I have a question about this. So if I just take one, so 2 blue edges incident to a vertex U, it kind of looks like I can just contract a single cycle and get a simpler proof. Like what's happening? I'm missing something, obviously.
Okay.
If I just take two edges, so let's just pretend it's 2 connected for now. So I just take 2 edges incident to the center vertex, and I just take a cycle through there. It kind of looks like you're just contracting one cycle.
Yeah, you're right. This is a simpler proof, except then you have to have at least 2 edges, and we need to solve the case where we have 0 edges also. Right, like we can't get away from solving the case.
Oh,
you need the 0, because once you contract those, now your new problem has 0 edges in S. So yeah, so maybe I'll draw. So you have your U, and you found this beautiful cycle, I don't know, in U, and you contract it, and you get this new graph and this is my U prime. But all of the edges here, I need them to not be in the Z2 flow. They need to be
Okay.
in the Z3. And so you have to solve that case. And so what this is oh, I see, it's like very slow. This part is the case that you need. It's the only case that you need. But then what I was just showing down here is that you can also play around with the parity of the edges
Okay.
into a vertex if you want. Any other questions? Okay, and then the last thing, this is the theorem of Tutt from 1954, and he used this to prove flow coloring duality. It's probably very well known, but I wanted to say it because it's just not in the paper, and it's kind of important. So basically, if you have a Z mod K flow, you can get a K flow in your graph. And we found a Z2 cross Z3 flow, but in this part it's really easy because Z2 cross Z3 is isomorphic to Z6. And so I'm going to assume that we have this like ZK flow, K could be equal to 6, and then you get what we need. And now we're going to get a K flow. And so what we do is in our graph G, we choose a ZK flow so that the total sum on of the boundaries that are positive is smallest, or maybe the total sum of the absolute value of the boundaries is the smallest you can. Sorry. Okay, so if it's 0, if the sum of the absolute value of all the boundaries is 0, then we really have a K flow. Maybe I said this badly. So I choose a ZK flow, but then I add the boundaries in Z. Okay. Okay, and so then so we can say, well, there must exist some vertex that has positive, we'll say positive boundary. We'll call that V. And then we look at, okay, where can we get from V in the rest of the graph? And I want to walk from V only forwards along edges, and I want to walk only on positive edges, positive flow values. This is easy. First, I'm going to fix the flow values so they're all positive. I'll just like reverse the direction if it's a negative edge. And so then I walk from V, and I get a positive flow value, and I see where I can get. And I argue that I must be able to get to some vertex V prime that has a negative boundary. Why? That's because say I didn't, then I end up finding an edge cut. This edge cut in the graph, and this edge cut has flow only going this way. It's positive, so it's non-zero in the integers, which is fine, except the flow across any cut is actually equal to the sum of the boundaries inside that cut, and since it's all positive, we have to have a flow boundary that's positive for weak and negative. Saying that properly. Okay. Anyway, okay. So the point is that we end up getting this V prime that has negative boundary. And then what we can do is we can push a flow of K backwards along all these edges. from V prime to V. And so that it changes the boundary at V by adding K. All of the vertices that are on our path, the boundary doesn't change. And then, sorry, V prime, you add K, and then at V you subtract K. And so you just made the absolute value of the sum of your boundaries in your graph smaller. And so you kind of improve things, and you can do this until you get an integer float. Okay, that was all I had. Thank you for listening.
Okay, thanks. So before we move to questions, maybe everyone could unmute and we can thank Kathryn for a lovely talk. On 3, 1, 2, 3. Okay, do we have any questions?
Yeah, a question here. Just wondering, is it well known for what other groups you can always find non-zero flows?
To like it just in any graph?
Yeah, or in a suitably connected graph.
Yeah. So so if your graph is 2 edge connected, we know 6. The conjecture is 5. I think once you get to 4 edge connected, there's a spanning tree argument. Somebody probably can help me with this. 4 edge connected has 2 disjoint spanning trees, so you get a Z2 cross Z2 flow. So I think 4 edge connected has no 0 4 flow, and the conjecture is 3. I think that's Tut's conjecture. Somebody interrupt and tell me if I'm wrong. So those are your 2 edge connectivities, and then your 2 edge connected bumps up to 3 edge connected really easily, and so I think 3 edge connected would fall in the same as it's Tut's 5 flow conjecture. So conjecture is 5, and we know 6.
Perhaps it's worth saying that Tut proved that it's just the order of the abelian group that matters.
Yes.
So
yes,
any abelian group with n elements has the same number of flows.
Okay, that's good to know.
I mean, that's what I think your question was, isn't it, Mo?
Well, yeah, just wondering about weirder groups than the sort of cyclic groups that were looked at here.
Yeah, and that's I mean, the point is that the number of flows is a Tut invariant, and it's a Tut invariant irrespective of which group you use.
This is kind of related and also semi a question, but I know non-abelian flows, you can consider them if you're doing embedded graphs because you have the fixed cyclic ordering, so you can have the non-abelian groups, the flow be well defined. Is there any work on knowing if there are any graphs that must have certain non-abelian flows, embedded graphs, or is this not interesting?
Well, I actually don't know about any work in that direction. I haven't come across it, so maybe somebody else has.
This is work by Goodall, Krajewski, Recht, and Vayner, maybe in the past, so maybe 2020 or 2021.
Okay, yeah, that sounds very interesting. I haven't considered it, so.
Any other questions? Okay, I'll stop the recording and we can move to a more informal discussion.